All right, thank you very much. So I looked at Sasha's list of quotes from Joseph. I don't have much to add, but in some way this talk will adhere closely to these directives. All right, so this talk has two parts. One's global, the other is local. The global is a kind of old story, which is 5 years old. It'll serve as a reminder and motivation, and then I'll pass to the more speculative local part. Okay, so let's start. So let's say Y is algebraic variety or algebraic stack over FQ bar, but defined over FQ. So we consider the category of constructible l-adic sheaves. Well, I'll write, so they're not really constructible, it's int-constructible. So you int complete, you allow arbitrary direct sums and cones thereof. So this is the basic object of study. And inside this category, if I like, so this denotes compact objects, these are really constructible sheaves. Right, so what we consider, so I'm reminding you what this Grothendieck's dictionary of sheaves to functions is. So inside here, we consider objects with a Weil structure, and we take case 0 of that. And the classical Grothendieck's sheaf to function correspondence is a map from this abelian group to the space of functions. If Y was an algebraic stack, I should say, I put here finite compact support on the set of FQ points of Y with coefficients in Q bar. So, however, you can do much, much better than that. And so, like, case 0 is, in some sense, is a very coarse invariant. So what one can do instead is the following. We consider this as a category, and instead of writing Weil sheaves as a sheaves equipped with an isomorphism, with its translated by the Frobenius with itself, we consider this as a category acted on by the Frobenius endomorphism. And in this case, it makes sense to take categorical trace. So it's a form of Hochschild homology. So if anytime you have a category, which is reasonable, let's say compactly generated, and the functor, you can take its trace. Again, it's Hochschild homology, and you obtain the vector space. And you can refine Grothendieck's construction to a map out of here to the same target. And in fact, there is a map from here to here. It's called the class map, and the triangle commutes. And so this is the fundamental arrow. So the problem with this arrow is that it's very far from being an isomorphism. So this thing on the left is huge. So what will happen in about 10 minutes will modify the sense in which we take the trace, that will make this arrow an isomorphism. But this modification is still not something that we really want. So what I'll do now in the global story will do something else to this arrow to make it an isomorphism in a particular situation. So now we take a specific example of Y. So okay, please tell me until what point it's visible when I write, because it will be going down. That's the end. All right. Till the end. All right. So X is a curve, again, over FQ bar, as usual, always assumed to be defined over FQ, and G is an algebraic group. And we consider what we call Bonn G. It's the moduli stack of G bundles on the curve. And this is what will take our Y to be. All right. So now inside, let me just continue a little bit here. So we consider this entire category sheaves. Yeah, let me say that what appears on the right-hand side, on G, if you take FQ points, this is the set of isomorphism classes of G bundles defined over the finite field, and this is the automorphic space in the unramified situation. When you study automorphic functions, it's functions on this space, unramified ones. All right, so this is our right-hand side. Now let's look at the left-hand side. So we can consider the entire category of sheaves in Bun-G. This is a very interesting category. You can call it the category of automorphic sheaves, but it turns out that there is a distinguished subcategory there, which was first discovered by Lomond in 1987. I don't know how he came to it, but then it resurfaced many times. And so it's denoted as follows. Say again? Yeah, so there's an analogy with character sheaves. So the subscript here is nilp. These are sheaves with nilpotent singular support. So this is, well, you have an l-adic sheaf, you can attach to the singular support in kind of the usual sense. It's a subset of the cotangent bundle, and nilp is a nilpotent cone in there. So this nilpotence condition appears in various places in representation theory, local, global, and I don't know if there is really conceptual explanation why it appears. Like, well, Sasha says it appears in character sheaves, many places. And let's consider this category. And for many years, so this category has been known for many years, but not many structural results were proved about it. But here I'll quote one that's relevant to this story. So what we'll do, we'll look at this map, but restrict it to this category. So let's consider this arrow. So we consider trace of the Frobenius on all automorphic sheaves. So this is functions with finite support on our automorphic space. But we'll precompose it with the inclusion of the subcategory of sheaves with nilpotent singular support. And so the theorem, and this is this series of papers AG, KRRV. This is Arinkin, myself, Kazhdan, Raskin, Rosenblum, and Warshawski. So the theorem says that the composite arrow is an isomorphism. And it's a kind of surprising theorem. It gives you a direct relation between automorphic functions and automorphic sheaves. It says that there is an algorithmic expression, so take the category of automorphic sheaves and apply the trace of Frobenius. So like if you prove some property on the categorical side from it, you'll be able to deduce formally a property on the function theoretic side. Let me just, by analogy with character sheaves, let me also quote an analog of this. So you can take the trace of the Frobenius on the category of, let me say, character sheaves on the adjoint quotient of just the group. There is no curve around. This is here with purely in representation theory. And an analogous thing happens. So you can map it to the trace of the Frobenius on all sheaves. And here there is a map to functions on the set of conjugacy classes. So G and G of FQ. And again, here, this is also an isomorphism. So this says that class functions are also the trace of the Frobenius in the category of character sheaves. Okay, So so now I'll quote another result that tells you that this theorem buys you already something very concrete for the Langlands correspondence. So yes, it's a PDF file of Warszawski, Rosenblum, and myself. It's available. And I can, with clear conscience, I can blame Nick for not writing down some foundations. It would have been a paper had he written, well, he says he's working on it. So let me, so now combine it with geometric Langlands and get something very concrete for automorphic functions. So, so geometric Langlands conjecture, which hasn't been proved in full for l-adic sheaves and characteristic 0, but I'll tell you exactly what is written. So what it says is that this category, as written, I'll have to introduce another object. So there will be two corrections. So I'll write something very coarse. So I'll write quasi-coherent sheaves on the appropriately defined stack of local systems, which I will define in a second. So let me write log-sys G-check restricted. I'll define this object, what it means. It's basically the only object in algebraic geometry that classifies local systems in the l-adic context. So that's what it says with the following two corrections. Well, first, it's not quasi-coherent sheaves. It's some modification that has to do with singularities of this thing. And we'll write incoherent sheaves with nilpotent singular support. So this nilp should not be confused with this nilp. This is the constructible singular support. This is coherent singular support. If you don't know this theory, forget it about it for now. Just pretend that these are quasi-coherent sheaves. So what we know for now is that it's what's proved that it's fully faithful. We don't know that you get the whole thing, but the conjecture says it's the whole. So these are the two modifications. Let me say what this guy is. Pardon me? Restricted. And I'll define what it is in a moment. So it's an object of algebraic geometry over the field of coefficients, which is QL bar. So I have to say, and I follow in Grothendieck, what its points are for QL bar algebra. And this is what they are. Home from spec R to this log-sys restricted is right exact symmetric monoidal functors. We define it in the Tanakian way. Functors from rep G check as a symmetric monoidal category to the category of R modules within sheaves on the curve with zero single support, otherwise known as lease. Just one has to be a little bit careful. So when I say sheaves, I always mean incompletion. So we take local systems and then we kind of incomplete, which allow arbitrary direct sums, and we take R modules in that. So, and R is, well, a priori infinite dimensional over QL bar. It doesn't mean that when I act on a local system, I preserve the actual local system, which is kind of with finite dimensional fibers. So like this R acts on the entire inductive system. So it's a little bit subtle object. It's R modules within this category. And so it's a little bit bizarre as an algebra-geometric object, which is why it hadn't been discovered many years ago. Let me tell you what it looks like. So I'll write here. So, and by the way, this makes sense in an arbitrary sheaf theoretic context. It doesn't have to be l-adic sheaves. You can do it for holonomic D modules. You can do it for constructible sheaves in the Betti. So it is disjoint union over isomorphism classes of semi-simple local systems of connected components, really splits as a huge direct sum. And there, so, and within given semi-simplification, it is what you think it is. So basically, kind of, so the problem when you try to define the modular space of l-adic local systems is that it's not clear how to vary them in families, because l-adic sheaves are by definition something profinite, and this R is a QL-bar algebra, which is not finite dimensional. It's not clear how would you combine these two things. It turns out that if you want to move in formal directions or in unipotent directions, that's not a problem. And kind of each of these connected components really allows you to move in unipotent and formal directions. But you cannot jump from one semi-simple local system to the other. And so that's why they come in disjointly. And again, it's a huge disjoint union, and it's a little bit counterintuitive. It's not clear why such a thing would be helpful, but it turns out that it is. Anyway, GLC says that these two guys are equivalent as categories, and now let's combine it with this theorem by taking the trace of the Frobenius on both sides. So when you take the trace of the Frobenius, according to this theorem, the left-hand side becomes functions with compact. So these are really automorphic functions. And this is what Langlands wanted. So he wanted to understand automorphic functions in terms of Langlands' dual side. So, and now let's take trace of the Frobenius here. So if it were quasi-co, if you take a stack with an endomorphism, and if you take quasi-co, if you take the trace of this endomorphism on the category, what you'll see sections, you'll see global functions on the set of fixed points. However, it's not int quasi-co, but int-co, and instead of sections, global functions, which are sections of the structure sheaf, you'll see sections of the dualizing sheaf. So it's a little miracle happens that has to do with this. So the consequence of the combination of two is that this is isomorphic, the space of global sections, on something that I'll denote log-sys g-check arithmetic, which is by definition, so log-sys arithmetic, which is a specialty of the l-adic situation over a finite field. I take log-6 restricted, and I take Frobenius fixed points. So this guy classifies Weil local systems as we know them, and it gives us an algebro-geometric structure. So what it says is that it's sections of the dualizing sheaf. And this is in some sense, well, this is the final answer to the Langlands program in the unramified situation. So it tells you the space of automorphic functions in terms of Langlands dual group is that. Exactly. So it turns out that there is none. And so this would be on the entire int-co, and the claim is that it's int-co-nilp is the same thing. The reason is the following, is that, so when you try to calculate this, you will encounter elements in the cotangent, elements in the Lie algebra, such that if you multiply them by Q, they become conjugate to themselves, and that forces nilpotence. So that's the miracle. So I'm saying that if you have a element of Lie algebra, if you scale it and scale it by non-1, and it stays conjugate to itself, then the element was nilpotent. So. Bonn G. So there's no level structure. These are Bonn G of Q is the unramified automorphic space. It's the Adel group modulo rationals modulo the maximal compact. So that's why it's unramified. All right. So that's where we wanted to arrive in the global and ramified situation. And now I'll start talking about the local story. Any questions about that? All right. So erase this. Yeah. Good question. I don't know. So a posteriori that follows? But no. I never asked myself this question, but like on the spot, I can't see that.
Yeah. I'll try to find what it said that before.
No, 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 it's not a bijection. Oh, like on K0. No. Yeah, so this is an isomorphism. Yeah. Great question. None. At least for now, none. So we really don't know. If you erase nilp, we don't know what to put on the right-hand side. So far, the current state of knowledge is that we only understand the Lang's interpretation of this for l-adic sheaves. For D modules, there's the whole different story. If it were dealing with D modules, the entire category of D modules would be isomorphic to int co on the entire log-sys on the entire de Rham version. Yeah. So like for l-adic sheaves, that's all we have. And it's a great question, like, can you go beyond? All right, so let me start with a local story. I don't know how far I'll get because like it's a lot of things to say. So local context. So we studied loop group. So think of loop group associated to a point on the curve. So we consider its points with values in a ring R. This is by definition points of the group G with values in the ring of Laurent series in R. And so the object of study is kind of a categorical upgrade of the category representation of the group. So what we want to do, we want to study categories on which the loop group acts. But now let's try to assign a meaning to it, and let's even forget about the loop group. Let's talk about even a finite dimensional group. And so there we'll run into trouble. So here is a naive definition. Well, you consider I'll be writing G. We consider sheaves on G, and convolution gives it a structure of monoidal category. And you can consider categories with an action of this monoidal category. You consider modules for this. So the claim is that this is a bad definition, and as I'll explain in a second. So just if you consider this, even at the naive level, the associativity structure, the fact that the action is associative is too weak, and as you'll see in a moment. So here's an explanation. Let me draw it here. So instead of talking about action, we might as well talk about coaction. So this thing is dualizable. So let's draw the diagram for associativity. See, so here's your category, and so a coaction will be this. So sheaves on C time, and this is the tensor product of categories as defined. It's Louis tensor product. All right. So what does associative mean? It means the following. So let's call it coaction. Let's iterate it here, so it's not a tensor identity. And so here is coaction. Okay, and here what you want to put is pull back with respect to the multiplication. But the problem is that the pullback with respect to multiplication doesn't go here. What it goes to instead, it goes to sheaves on G times G. And so these categories are related. So there's a fully faithful embedding. It admits a right adjoint. But if you consider any reasonable example, this diagram will not commute. Just if you take C, something sheaves on the variety in which the group acts, this will fail to commute. What will commute is if you apply the right adjoint. But there you see that you're losing information because this right adjoint kills stuff. So demanding the commutativity of this diagram is too weak. So you don't want to do that. So and the failure for this is what we call the failure of the categorical unit formula. So if you're dealing with constructible sheaves, if you consider sheaves on Y1, tensor sheaves on Y2, it admits a fully faithful embedding to sheaves on Y1 times Y2, but this fully faithful embedding is not an equivalence. It would be okay for D modules, it would be okay for Betti sheaves, but it's not okay in the constructible context. So therefore, this is not a good definition and one has to change it. And I'll explain now how to change it, but that will entail its own problems. So the device that I'll explain is due to Drinfeld. And it's a very formal device. See if I'm forgetting something. So what Drinfeld says is this. So initially, we consider the world of DG categories. There's this C's with its symmetric monodal structure. Instead, we'll consider a different world. When I say world, it's another word for two category. I'll call it DG cat algeom. So this is the world that was introduced by Drinfeld. And so here's what the objects are. Objects are no longer just DG categories. These are families. So an object here, let's see underlined, is an assignment. For every affine scheme S, we consider a category that I'll denote C underlined sub S, on which sheaves of S acts. So it's a module for this. And we impose how these guys interact for different S's. So such that, so for every morphism S1 to S2, we give ourselves a functor CS1 CS2, F lower star, and also a functor F upper chic. And this functor, both these functors are supposed to be linear with respect to the action of sheaves on S2. So we give ourselves this whole system. So here are examples. So if you start with a stack, you can define a notion that I'll call sheaves underlined Y, whose value on S is sheaves on Y times S. So when we want to encode sheaves on Y, now we do it in all families. We allow it to parameterize. So that's one example. Another example is kind of stupid example, but it's very important for us. So there is a fully faithful embedding that I'll call embed restrict. So namely, if you start with just a plain DG category, we can define an object of DG cat algeom as follows. Its value on S is just C tensor sheaves on S. And typically, guys in example 1 are not of the type of the type explained in example 2. We call the essential image of this embedding restricted. So these are these algebro-geometric categories that are of this very artificial nature. However, there is a class of stacks for which this guy is in the image, and so these are called restricted stacks. And they occur essentially if and only if it's never occurs for algebraic varieties, occurs of stacks which have discretely many isomorphism classes of objects. So example 3, if Y is something like G mod B mod N, so our favorite object in geometric representation theory, it's restricted. So sheaves on this guy is restricted. No, G mod B is also like, this is slightly bigger. Yes, yeah, this is good. Another example would be Y, which is Bonn G on P1. So here there are not finitely many orbits, but they're discretely many orbits. It's like infinite union. Or you can consider Y to be the affine-Grassmannian modulo the positive part. So it's the place where geometric attack occurs. All of these guides are restricted. Yes, yeah. So this, yes. What I want is, it's not discrete. I want there to be on every quasi-compact bit, I want to be finitely many orbits. That's all I want. So only in that sense. All right. So I'm sorry, my usage of Blackboard space is terrible. Let me now say that, so one can endow, so the whole idea of Drinfeld's was to endow this with a symmetric monoidal structure. Uniquely characterized as follows. So in some sense, this category is generated by guys of the form sheaves underlined of affine schemes. So it's enough to define structure in those, and we define as follows: sheaves underlined on S1, tensor sheaves underlined on S2 is by definition sheaves underlined on S1 times S2. This is a definition. So we kind of, so this categorical unit formula failed on the nose, but we force it to take place in some larger world. So that's what we are doing. And so with these definitions, we so we define LG cat to be sheaves underlined LG mod, but inside DG cat LGOM. So the problem that I alluded to here goes away in this larger world, and that's what we do. So let me also, as a remark, say something about this trace of the Frobenius. So we could have taken trace of the Frobenius also in this larger world. So we could have taken on sheaves underlined Y and understood within the symmetric monoidal category DG cat LGOM. And we would have gotten the same answer. It would be sheaves. So like in the world of DG cat LGOM, you do get automorphic functions or whatever without, but the problem is that we are not working with DG categories, but with these weird guys. And in some sense, for any Y, yes, yeah. Before, it's in a different context. It was in DG cat. And this is true in DG cat LGOM, this is always true. For tautological reasons, if you wish. It doesn't have, it has nothing to do with the Frobenius. It's for any endomorphism. Completely formal. It's sheaves underlined. Yes, that's so. This DG cat LGOM is any constructible in any constructible sheaf theory. All right. Okay, so all of this is well and good. What's the problem? The problem is that you cannot connect it with the Langlands dual side, because on the Langlands dual side, whatever it is, in the global context, it was actually a category and not an object DG cat LGOM. And what we will see that in the local context, it will be a two category, but this is two category that lives over dgcat, not dgcat algeom. So these guys, dgcat algeom, are still too large to have any comparison with Langland's dual side. So we gave the definition. What we'll have to do now is to trim it down to something that has a chance to match with the dual side. So we enlarged the world, we obtained a good definition, but it's too large. So we'll have to go down. And now I'll explain the principle of how we do it. And let's do it first, not for the loop group, for the actual finite dimensional group. So the GB reductive, we consider GGcat as we defined it. And now I'll introduce a subcategory here that are called restricted. And here's the definition. So it might come a little unmotivated, but please bear with me. I'll try to motivate it. So definition, C underlined in GCat is restricted if the following happens. If I take its invariance with respect to the maximal unipotent, and you take invariance and you forget structure, it's just an object of dgcat algeom, I want that to be restricted. Is restricted, i.e., in the image of dgcat inside dgcat algeom. So basically, I'm saying the following, that so we have to consider dgcat algeom because the geometry of the group G forces us to. So there are these algebra-geometric directions that we can't get rid of. But so what I want is that if you, so I want to say that if you take this n invariance, it trims down, it kind of throws all the kind of junk that has to do with the geometry of the group. And once we do that, we don't want any more algebraic geometry. We want that to be just restricted. So that's our definition. So I'll now quote a little exercise. So let's take our group to be a torus. So in which case there is no n. And what I'm saying in this case, I want to call a category restricted if it's restricted just as if the underlying category is restricted. So let's see what it buys us. So lemma is the following, that if, so let's say it like this, an object C underlined in dgcat, well, I don't have to like underline because it's actual category, in Gmod restricted splits as a direct sum of isotypic components by character sheaves. So kind of just to save time, I won't go into too much details. So like if you have a character sheaf, you can define an action of your torus on vect. And basically what I'm saying is that any C which is restricted, which such the underlying category is restricted, splits it according to characters. So you don't get any families. So like it really splits as a direct sum. All right. Okay, so let me see how I'm doing on time. So now we want to define what it means to be restricted for loop groups. And that's not so easy. So like if you were to impose something like this, you won't get the right definition because there is cuspidal stuff. So if you impose invariance with respect to loops into n, you lose all the cuspidal information. So here, the fact that this works has to do with the fact that in a finite dimensional situation, everything is Eisenstein. And so it's not at all easy. So we didn't know the definition for 2 years. And recently, the definition has emerged. And that definition uses the Moy-Prasad theory and its refinement by J.K.U. and Finson. And so the final stretch was the push by Warszawski, David Young, and Gurbier Dillon. So I won't be able to give the definition. I'll give it for SL2. So here's how the definition for SL2. So the first observation is that this entire category is a rising union over depth of subcategories that have depth less than k. So there are these inclusions, and these inclusions admit right adjoints. So one can talk about categories exactly of depth R. It's a rational number. It's exactly the same as in the classical theory. So depth less equal to k if there exists a vertex in the building such that you haven't, if your category is generated by objects fixed by the Moy-Prasad subgroup k plus, if you wish. It's exactly like in p-adic groups. There's no difference. So C is restricted if, first of all, its components of depth exactly k are all restricted. So as I said, so this is a filtration of the two category, and these inclusions admit right adjoints. So every LG category admits its own filtration with right adjoints. You can define subquotients, and restricted means that all the subquotients of given depth are restricted. So this is true. This will be the case also for groups other than GL SL2. What's specialty there? The specialty of SL2 is the next step. Otherwise, there is inductive procedure. So now there is an analog of Moy-Prasad theory describes us the category of given depth precisely. And what it says is the following, that this category is actually equivalent to representations of a torus of the same depth, where T is split if K is an integer and T is ramified. So there's only one conjugate is a class of ramified tori for SL2 if K is half integer. So there are only two types for SL2. There are only two types of K that can contribute. There are integers and half integers, and so there is an equivalence like this. You can prove it directly. So it's basically part of Howe's theory. It's not. I mean, it's the cat. So the claim is that the categories of depth K, this two categories is equivalent to the corresponding category for the torus. But which torus you take? So this is that two category of categories with an action of LG of depth exactly K. Cat. And now restricted means that you're restricted here if you're restricted here, and here, because this is commutative, we already said what restricted means. It means that just the underlying category is restricted. So the passage here is some kind of Heisenberg game. So this passage here does not preserve the underlying category. So there's some Heisenberg group involved, and you take invariance with respect to some Lagrangian. And for a group of higher rank, it's iterative procedure of the same kind. So the difference is that you will have not, so this T is what's called a twisted levy, and in general you have a sequence of twisted levies. So you go down in rank. Just in SL2, you stop here. All right. All right, so now in the remaining this one, no, for SL2 it's very easy. You'll see this Heisenberg in one step. In general, it's serious work that that has only recently been announced. So this is Yasha and David and Gurbier. All right. So, and now we'll go back to our trace calculations. So I asked David, they couldn't vouch for it. So there is Fin's and Yu classification of representations of the PID group along these lines. So Fin's and Yu don't give you an equivalence of categories. And it's a legit question. So this is equivalence of two categories. The question is if you have an equivalence of categories for PID groups. They couldn't vouch for it, but so they said it's probably true. So they didn't tell me that they could prove it in the classical case. No, they can talk about any. So for SL2, this is definitely true. Pardon me? T is a torus, but it can be either split or non-split, depending on what if K is. Pardon me? Yes, yes. So here is which torus it is. It only depends on K. If it's like integer, half integer.
This is a categorical. Find the linguistic.
It's not the linguistic theory. It's not inductions. It's really not the linguistic theory. And it's a super cool kind of direction to understand what it has to do with the linguistic theory. And there's a paper of Bezrakovnik and Charlotte Chan that goes in this direction. But it's not that. Yes. Yeah, this is really Moy-Prasad theory. It's refinement of House theory from. In some sense, it's much less fancy, but and much more combinatorially involved. So that's what we've got for now. It's not ideal to have this definition, but that's what we have. I have a quote from Eitan from 30 years ago exactly about this, but we'll leave it for later. All right, so final stretch will take, so the two things I want to add, one is taking traces and the other is local geometric Lagrange and local classical Lagrange. So like counterparts of what I said in the global situation for the local situation. So we'll begin with the warm-up. We'll first consider the finite dimensional reductive group. We consider GCAT not restricted, and we'll take the trace of the Frobenius. Well, in fact, G can be completely arbitrary here, but in the sense of DGCAT algeom. But the same tautological reason, as I said, that if you take trace DGCAT algeom of the Frobenius, what you'll see is the following. It will be sheaves underlined as it should be. So this is a G. Sheaves underlined on G, but the stack divided by Frobenius twisted conjugacy. Now, if G is connected, Lang's theorem tells you that by Lang, this is the same as point divided by FQ points of G. And this stack is restricted. So therefore, this is, you can think of it just sheaves on point mod G of FQ, otherwise known as representations of FQ. So what it says, it's something, sorry. So something happened. It says that if you consider this two category of guys with an action of G as a group, categories. If you take the trace of the Frobenius, you recover the classical object, which is representations of the Chevalier group. So something already happened. So like we recover something one categorical down from a two categorical statement. And then this is DG cat algebra. It's not, again, by definition, not too interesting. However, so theorem, trace of Frobenius on G cat restricted, and this is trace taken in categories, not DG-cat. There's no longer DG-cat algebra nonsense. This is really a two category enriched over DG-cat. We take trace of Frobenius. The claim is that you get the same thing. So if you consider this category that I defined, on it, there's direct relation between this two categorical object and the usual category representations of the Chevalier group. So just let me make a brief digression. Instead of Frobenius, I take the identity. So similarly, if you take the trace of identity on, in the sense of DG-cat algebra on G-cat, what you'll see sheaves underlined on G mod the adjoint quotient. And so again, complete tautology, but here comes the theorem that if you consider trace in the usual sense of identity of DG-cat restricted, you get sheaves, you get character sheaves. So character sheaves define ballistic, however, like there are many, many definitions, but the categorical meaning is the following, that if you take this particular two category, if you consider trace of identity, on that, you'll recover character sheaves. So in that sense, so like this is what character sheaves are. All right, and now we'll go to the loop group. So if you take, again, tautological statement, if you take the trace in the sense of DG-cat algebra, DG-cat algebra of the Frobenius on all categories, you will get, well, just like here, sheaves underlined on LG modulo Frobenius twisted conjugacy. However, Lang's theorem is inapplicable to loop group, and this is something interesting. It's really loop group modulo Frobenius twisted conjugacy. It has a name. It's called the stack of isocrystals. And you can look at it and you'll see that it's restricted. So we might as well delete the sheaves underlined. And this is the stack that appears in Fargues-Scholze, the algebro-geometric incarnation. So this is an object of interest. So now comes a conjecture, which is the counterpart of this theorem of AJK-RV that I quoted. This is a local analog of the global conjecture. And that says that if you take the trace in the usual sense on the restricted category, like here, this versus this, you'll get the same thing. So it says that if you consider this world of restricted categories, you consider the trace of the Frobenius from that, you'll recover sheaves on isocrystals. So that's conjecture number one. So now I'll state very cool. I don't know. I believe that it has something to do with loop character sheaves, which I don't know what they are. I get a definition, yes, but these have been studied by Kazdan and Barshavsky and by Bezrukavnikov and Chan, so there is something to study here. Oh, then you'll get just all sheaves on LG modulo LG conjugacy. Yeah, this is always true. This can. All right, so like there are one more thing to say. So now I'll state the local geometric Langlands conjecture. It's of two categorical nature. So geometric side is LG cat restricted, and it really has to be restricted because non-restricted guys have no counterpart on the other side. So naively, what I should say I would say the following. I consider log-cis restricted on the puncture disk. I'll consider quasi-co of that. It's a monoidal category, and consider modules. And this is false for the same reason as it was false in the global situation. I have to replace quasi-co by int-co. So we write 2 int-co, whatever it means, nilpotent single support. It's a theory that was developed by Arinkin. It's some kind of modification of the notion of category acted on by quasi-co. So this is local geometric Langlands conjecture. And which is surprisingly not so far from being done due to work by David Yang and Gurbir Dillon. Now let's combine these two. Let's take the trace of Frobenius on both sides. So corollary, you obtain that sheaves on isocrystals. And when you compute trace of Frobenius here, you will discover int-co on the arithmetic version, log-cis g-check arithmetic on the puncture disk. So if it were quasi-co, here you would get quasi-co, but because it's int-co, it's int-co. And this is Fargues-Scholze, algebro-geometric version. So basically what I'm saying is that if you combine this trace conjecture with a version of geometric Langlands, the local case, but by taking the Frobenius, you recover the equivalence of Fargues-Scholze. So the Fargues-Scholze are actually one level down consequence of something that happens to categorical level. So I'm done. Yes.
So is there a version of this in the analytic?
I don't know. Great question. So it's not clear to me how you would define this two categorical gadget in the analytic context. Farg said that he would think about it, that even he had ideas, but I don't know what happened. It's a great question. But that's the reason why I prefer the algebra-geometric version, because it gives you direct passage. Oh, okay, yeah. Please.
Conjecture for the geometric settings, like
this is a great question. This is valid as is over C, as a conjecture, but over C you can ask much more. So then you do D modules, and you don't need restricted. So like this categorical unit formula holds, and all this nonsense about restrictedness goes away. You consider LG module categories naively. So that's what you consider on the left-hand side, and on the right-hand side you consider just the RAM version. And so there is that version. Like in the global situation, it was all D modules on Bungie versus incoherent sheaves on the RAM version of log-cis. Similarly here, you have a much more ambitious statement. All guys versus log-cis non-restricted on the RAM. But this one is supposed to be much simpler. Because otherwise I can't define. So you see, I have to say what is a category with an action of LG. And so what do you say? Okay. No. Okay, sorry, I should have said that. So here's an example. Forget loop group, consider the finite dimensional group. So here's an example. Consider sheaves underlined on G mod B. This guy, as a category, it's not restricted. But if you consider it as a representation of G, it is restricted. Because if I take, as I said, G mod B mod N, it has finitely many orbits. Yeah. So you see, like this is kind of the smallest representation of the finite dimensional group that I want to consider, apart from the trivial one. And it has this underlined in it. So it has this algeom component. So that kind of, I am forced to consider these guys. DG-cat algeom is the framework in which they exist, but then I trim it down. Yes. Take an invariance, right? No. In this case, yes. Correct. With an actual, yes, and that's the point of view that Gurbir explained to me, that in fact you can take this route and you can define restricted categories without ever mentioning DG-cat algeom. You can also in the loop group context. It just feels a little bit less natural. So I was debating whether or not I should explain this point of view or that point of view. So in that point of view, you get a bunch of algebras. But you're right. Monoidal categories. So yeah. So you can think of it really as categories with an action of something, of this monoidal category. Yes. So this is a valid definition which avoids the mention of DG-cat algeom.